Okay, so now we're recording. And we will share a screen. Okay, so now we're all set up. Are there any questions about anything before we get started? No? Okay, so let's just briefly summarize what we've done last time. We get a new page. Last time, we just sort of took stock of all of the properties that should hold for forking. So we proved that the forking relation satisfies the following properties. So one is that you have, what was the first one that we wanted? Well, it doesn't matter. I'll say extension first. This was in any case the first one we proved, which is that if A is independent over A with B, then given C, I can extend A, or I can extend the type of A over AB to A prime, such that A prime is independent over A, not just with B, but also with C. So maybe I change the element, but preserving the type, I can extend my type to something which is bigger. Now, this is a little bit like what happens in, I don't know, if you've done algebraic geometry, you like pick generic points. So, you know, you like have a variety which is defined over some field, and then you extend to a bigger field. And what do you want to do when you take a generic point? You want to pick a point of your variety. You know, you have some set cut out by polynomial equations. When you pass to this bigger field, you want to pick a point of your variety that isn't caught in a proper subvariety defined by these new field coefficients. So you have new polynomials, new varieties that you could trap your element in. So to pick a generic point, what do? You land in the old variety and avoid all of the new varieties, all of the new varieties of proper subdimension. I mean, of properly smaller dimension. And as a consequence, you know, you don't have the dimension drop or anything. So it's a similar idea here. When I move from a small set of parameters to a bigger set of parameters, I, in principle, could trap my element into a smaller set. For example, I could add an equality that I didn't have before. And so the non-forking extension says that I can extend my type to this larger parameter set in such a way that I avoid any such trapping. Okay, so that's extension. 2 is base monotonicity. Which says that if A is independent with A, BC, then A is independent over AB with C. So I can move things from the right-hand side to the base. 3 is left transitivity. And what does left transitivity say? This just says that if A is independent with C, plus B is independent with C over A and A, then A and B are independent over A with C. And this one is kind of technical looking. So there's going to be a natural way to interpret this once we get to symmetry. But we won't have symmetry in general. This relation of non-forking independence will be symmetric only in special contexts, namely the simple theories. So in fact, if the symmetry of the non-forking relation is equivalent to simplicity. So that's going to be the only context in which it works as nicely as we would like. But okay, we did this all last time. So what we're going to try to prove today is local character and Kim's lemma. And I want to prove Kim's lemma, assuming that Morley sequences exist. And then what we'll do is we'll sort of reverse engineer why Morley sequences have to exist. So let's start with Kim's lemma. Okay, So what does Kim's lemma say? And this is like a really, really, really fundamental thing, because it generalizes to other contexts, and in other contexts, it will be like the fundamental properties that we care about. So Kim's lemma, which is really a theorem, I should say, says the following thing. So it says, suppose T is simple. The following are equivalent. One is that phi x a divides over a. Two is that okay, let's say there is a Morley sequence I equals ai, I less than omega. And I have to tell you what a Morley sequence is. I don't think we've talked about it in this context. Over, oh, whoops. Okay, I wanted that there, but not here. With a0 equals a, such that phi x ai, I less than omega, is inconsistent. And three, for all Morley sequences, I equals ai, I less than omega, with a0 equals a, phi x ai, I less than omega, is inconsistent. Okay, so before we delve into what this means exactly, what I would like to observe is that dividing is an existential condition. So what are you doing when you say that a formula divides? You say there is an indiscernible sequence with a certain property, namely that if you move your formula along that sequence, you get something inconsistent. Now, the big gain in Kim's lemma is that you convert dividing into something universal. So now instead of saying that there is a sequence, I can say for all sequences of a certain kind. So it might not be true, and in fact, it almost never is true, that a formula will divide with respect to every indiscernible sequence. That only happens actually when the formula is itself inconsistent. But you can say it happens for every sequence of a certain kind, and that turns out to be an extremely useful tool in the theory. So what is a Morley sequence? So we're going to prove this in several steps. So the first thing is, what is a Morley sequence? So here's the definition. So the A indiscernible sequence I, which is ai, I less than omega. Although I write it with omega to simplify things, but you know, it could be any linear order you like. It doesn't matter. It's an indiscernible sequence such that ai is independent from its predecessors over a. Oh, whoops. So I forgot. Okay, I think I'm a little out of it today. Sorry. Okay, the A indiscernible sequence I is a Morley sequence. If this holds for all I. Okay, so we're defining Morley sequence, and then the key condition is this condition here. which says that the ith thing is independent from everything that came before. Okay, so let's think about what this says, because this looks confusing, but it actually makes a ton of intuitive sense. So let's go back to an example we thought about when we were learning the definition of dividing, which is this definition of an equivalent solution. So we had A here and B here, and we knew that A forked with B over the empty set via the formula EXB, right? So we knew that this formula divided over the empty set. And the question was why? And the answer is because we could choose an indeterminable sequence like this, which went from class to class, and then saying I'm equivalent to this element in the indeterminable sequence, and I'm equivalent to this element in the indeterminable sequence, and I'm equivalent to this element in the indeterminable sequence. These are all pairwise inconsistent because the elements themselves are inconsistent. Now, if we chose a different sequence, which lived inside this class, then this formula EXB would be consistent along that sequence, because what would it say? It says I'm equivalent to this, I'm equivalent to this, I'm equivalent to this, I'm equivalent to this. Any element of that class will do, because they're all equivalent. It will satisfy all of those formulas. So when you want to understand what are the sequences that witness dividing in this example, you see that you want to take like the generic one, the one that moves between the classes, not like the specific one that gets trapped inside a small set, right? So the way to think about this is like, if you get trapped inside of a small set, then you're like a super non-generic kind of thing that happens on a set of measure 0. If you take a generic sequence, then that's going to be the kind of thing the witness is dividing. And again, this is a lot of intuitive sense. If you have a formula that divides, what does it mean? It means you want to sort of move it around inside your structure. You want to move it along some indeterminable sequence such that the instances become almost disjoint. I mean, the best thing is when they are disjoint, but normally you just get k inconsistent for some k. So how should you move it about to get inconsistency? Well, if you move it about in some small space, in a very specific space, then maybe you do get a lot of overlap. So the way you want to move it is you want to move it as generically as possible, and then you'll get very few overlaps. That's the sort of intuitive idea. So what does it mean to take a generic sequence? Well, as you're building your sequence step by step, you want to choose the new element that you're adding to your sequence to be free from everything that came before it. And what does free mean? It means it doesn't fork. Okay, so that's what a Morley sequence is. It's a way of taking a generic sequence. So here is an observation that I want to make. So this is not related to the proof, but it's worth noting. So suppose Q in SXM is a global A invariant type. Going back to what we did before, then if A realizes Q over A and B can be a really long tuple. I don't care that it's finite. Then A is forking independent over A with B. Okay, so let's think about why. So I think it should be clear for dividing that this is true. So clear for dividing. Why? Well, if A divides over A with B, then there is some phi xb in the type of A over AB such that for some indiscernible I, or sorry, that should be a BI. And I should say A indiscernible, BI I less than omega with B0 equals B, phi x bi, I less than omega, is inconsistent. That's what it means to divide. Now, because it's an A indiscernible sequence, so by A indiscernibility, we know that bi has the same type over A as bj for all I and j, right? I mean, if you move along an indiscernible sequence, then all the elements have, in particular, the same type. But what does it mean to be invariant? It means that if one formula goes in the type, then all of the other formulas that are defined with the same formula and parameters with the same type go in the type as well. So actually, all of these instances are elements of Q. One of the formulas was, namely phi x b0, so all of them go into Q. So Q is inconsistent, which contradicts the definition of a type. So what did we use here? We used invariance. So we knew that if phi x b0 was in the type, then because phi x b1 has the same type as b0, phi x b1 had to go into the type. That's what invariance says. And phi x b2 and phi x b3. So they all have to go in. So all of these formulas are in Q, but together all these formulas are inconsistent. That's impossible for a type or a subset of a type. Okay, so for dividing, this is clear. Now, if A forks with B, then there is some phi x b in the type of A over AB, such that phi x b proves a finite disjunction, I less than k, of C x ci, where each ci x ci divides over A. So if you fork, what does that mean? It means you imply a finite disjunction of things that divide. And those things have new parameters, right? Which were maybe not contained in AB. But what we can do is we can let C be a list of those new parameters. So we take the new parameters, call them C, and what we can do is we can let A prime realize Q, not just over AB, but now over C as well. So now these formulas, which had parameters in these new things, I mean, these new parameters are now parameters of the type that we're looking at. So A prime realizes phi xb because it realized the type of Q over AB, and A realized that. So there is some I less than K such that A prime realizes Ci x Ci. Because I put the parameters in there, and Q restricted to ABC is a complete type, the type has to tell me which formula to put in. It has to say, I pick this disjunct. And once it does that, that means it divides. So A prime divides over A with BC. And that contradicts the first observation. Okay. So actually, I mean, one way to think about the difference between forking and dividing is you always, I mean, forking and dividing are the same if you have enough parameters, right? Like if you if you fork, that means that you imply a finite disjunction of dividing formulas. Now, if your type in question, the type that forks, has those parameters inside its domain of, inside its parameters, then the complete type has to pick one of the disjuncts. So the real problem is when you have a type, say, over a certain set, and the formulas that it implies that fork have parameters that come from outside that set. If they came from inside, then because it's complete, it would have to pick one of the disjuncts, and then dividing and forking are the same. So that's basically one of the problems between moving between forking and dividing. Okay. So what is the point of all of this? The point, so the upshot, is that if, let's say Q is a global A invariant type, then if I equals AI, I less than omega, is a sequence such that AI realizes Q over A less than I for all I less than omega, then what? Then I is a Morley sequence over A. Okay, so when we were talking about indiscernible sequences, at the very beginning, we had two arguments for how you can prove that you can find indiscernible sequences that realize an EM type of a given sequence of elements. And one of those was to use a Ramsey-theoretic argument, and the other one was to create an invariant type and then realize it inductively. And the point that I'm making here is that what we were doing when we realized that invariant type inductively was we were producing Morley sequences. So this idea of a Morley sequence is something that we've seen already. It's exactly the same thing as realizing inductively an invariant type. Well, okay, I shouldn't say it's exactly the same thing, because it turns out that not every Morley sequence will come from a global invariant type. But when you do it in a global invariant type, then it will give you a Morley sequence. Okay, is that clear? So invariance is much stronger than being non-forking. It implies being non-forking. All right, so the first thing is that we've seen some Morley sequences already. Now let's make an additional observation. So this is a lemma, which I think is nice. So let alpha be an ordinal. The following are equivalent. So one is there is a tree, eta in omega to the less than alpha. Formulas, phi I, x, yi, I less than alpha, and numbers, ki, I less than alpha, such that two things happen. So the first thing is that for all eta in omega to the alpha, phi I x a eta up to I less than alpha is consistent. And B, for all eta in omega to the I, phi I plus 1 x a eta concatenated with j, as j ranges over the natural numbers, is k I plus 1 inconsistent. Okay, so that's the first condition. This is number one. And we'll draw pictures so that this becomes clear. But let me just state the second condition very quickly. Here, let me turn this. I think you might be able to get more of the screen. Okay, so you just said there is a tree. So I named the parameters, the numbers, and the formulas. And then the second condition, number 2, says there is a sequence I less than alpha, and formulas phi x, yi, I less than alpha, such that phi I plus 1 x a I plus 1 divides over a less than or equal to I for all I less than alpha. Okay, so this says if you have a chain of formulas that are dividing, each one over everything that came before, then you can build a tree of a certain height. So let's draw the picture of what's happening here, because the proof of this is extremely easy, even though understanding the statement is maybe the complicated thing. So let's draw a tree. So in our tree, each level will be decorated with a formula. So we have like phi 0, phi 1, phi 2, phi 3. And you'll notice this looks an awful lot like the tree property, right? So if I move along a path through this tree where I take the parameter at level 0 and I plug it into phi 0. I take the parameter at level 1 and I plug it into phi 1. I take the parameter at level 2 and I plug it into phi 2. So I'm moving along a path, plugging associated formulas, associated parameters into the associated formulas. I get a consistent partial type. However, if I fix a particular node, like let's say I fix this node here, and I look at the immediate descendants, these immediate descendants will be inconsistent with each other. And in fact, uniformly, ki plus 1 inconsistent, where I is the level of the purple node, and I plus 1 indicates the level at which this collection is taken. So in addition to decorating each level with a formula, I decorate it with a number too. So I should have written that perhaps, K0, K3. And so these things indicated in red, that family of formulas is not just inconsistent, it's K2 inconsistent. And if I looked at, say, these collections or this collection of formulas, they would be K3 inconsistent. So the level of inconsistency depends on the level you're at in the tree. This is some configuration. So, okay, if you have the tree property, then it's exactly the same thing, except at each level you have the same formula and the same K. So if you recall the definition of the tree property, what was it? It just said exactly that you have this configuration where the tree is height omega and you have the same formula and the same K. Okay. So this configuration is related to having a sequence of formulas, each of which divides over the previous. So what's the proof? So LS alpha, LS alpha is going to be the following language. So you have the tree partial order, the meet function, the lexicographic order, and then a collection of predicates, p beta, for beta less than alpha. Okay, so LS without the alpha is the same thing as LS omega. If you recall our discussion of indiscernible trees. So we can view omega to the less than alpha as an LS alpha structure in a natural way with the interpretation of P sub beta is just omega to the beta, sitting inside of omega to the alpha, less than alpha. So P beta will just identify the nodes at level beta. So these are exactly the nodes exactly at level beta. That's P beta. Okay, so notice this agrees with the definition of the LS structure on omega to the less than omega that we gave before. It just extends it to trees of possibly different height. And a fact, which is easy to prove on your own, is that LS alpha indiscernibles exist, i.e. Omega to the less than alpha indexed indiscernibles have the modeling property and we will call such trees, such indiscernibles, S indiscernible trees. Okay, so before we said that S indiscernible trees were indexed by omega to the less than omega in this language where I had omega many predicates that named the omega many levels. Now, does it matter that you have omega many levels? Well, not really, but if you have more levels, then you need more predicates. And it's extremely easy to show that if you have, a tree of height omega sub 17, and you want to find an indiscernible locally based on something indexed by omega less than 17, then there's a sort of easy compactness argument that you can deduce that the indiscernibles exist using that that omega to the less than omega indexed indiscernibles have the modeling property. Because in a compactness argument, you're only ever going to see finitely many levels, and you know that it's going to be true for even omega many levels at a time. So this is like a very easy thing to check, just using compactness in the definition of local basedness. So you can make sense of the notion of an S indiscernible tree, even when the tree is very tall. And in fact, when we get to NSOP1 theories, we'll have to do that, as you'll see. Okay, so let's do the argument now. So suppose one. So what we'll do now is we will do 1 implies 2. So suppose we are given our tree of tuples, eta in omega to less than alpha, phi I yi I less than alpha, and ki I less than alpha, then let a prime eta in omega to less than alpha, be an S indiscernible tree locally based on A alpha, on A eta in omega to less than alpha. So you started with some collection of tuples, and you just replaced them with the indiscernible version. So by local basedness, we still have the conditions A and B. Why? Well, because if something is true for every path, then that implies that whenever you take a tuple that has the quantifier free type of an n-tuple of things that line a path, the associated formulas are consistent. That will pass to anything which is indiscernible. What does it mean to talk about condition B? Well, that says like if you have, I don't know, ki plus 1 many elements in the level pi plus 1, and their meet pairwise is at level pi, then they're inconsistent. That's something that just talks about any collection of elements with that same quantifier free type. So local basedness tells you that has to pass to an indiscernible witness. So you still have conditions A and B. So now let's just observe what our picture looks like. We've got this tree. Like this. And we've got our formulas, phi0, phi1, phi2, phi3, so on and so forth. And each of these comes with some number, k1, k2, k3. And what do you know about this sequence? Okay, we're in an S-indiscernible tree, right? So this red sequence is indiscernible over the base node, over the node indexed by the empty set. And this sequence here is going to be indiscernible over this initial segment. And this sequence here will be indiscernible over, say, this initial segment, right? Because S indiscernibility will tell you that, okay, if I take an in tuple from here and an in tuple from here, they have the same quantifier free type over everything in the column below them, in the path below them. So they have to have the same type. That's what S indiscernibility says. So by S indiscernibility, we know that for all I less than alpha, the sequence A sub 0 to the I concatenated with J, as J ranges over the natural numbers, is indiscernible over A sub 0 to the less than or equal to I. So that's like everything up to that point. This is clear from the definition of S indiscernible tree. So then, because phi sub I plus 1 of x a 0 to the I concatenated with j less than omega, I mean, this is an example of the situation that B was talking about. We have a collection of nodes which are children of a common node. And we're looking at the I plus first formula. All these nodes have level I plus 1. So what does this say? This is k I plus 1 inconsistent. Hence, phi I plus 1 witnesses that phi I plus 1 x a sub 0 to the I plus 1, namely that's where the sequence starts from, divides over a sub 0 to the less than or equal to I. So the formulas phi I x yi I less than alpha and a 0 I less than alpha witness 2. What did 2 say? 2, let's go back so that we all understand why this witness is 2. What did 2 say? 2 says I have a sequence of formulas and a sequence of tuples. And if I plug in the I plus first tuple into the I plus first formula, that divides over all of the things indexed by things less than or equal to I. So let's go back and see the statement. So 2 said there is a sequence a sub I less than alpha, and formulas phi I less than alpha, such that if I plug the I plus first tuple into the I plus first formula, then that divides over everything that came before. So what's the idea? I start with the tree like this, I make it S indiscernible, and then I just look. I can take my sequence to be the all zeros path, and it's a bunch of dividing. And this to me, is the way that you should really think about what the tree property is saying. What is the tree property saying? It's just saying you've got a really long dividing sequence. And because everything has the same type in an indiscernible sequence, you can sort of move the dividing sequence a bunch to get a tree. And that's what we're going to see next. So now we'll do the other direction. So this is 2 implies 1. So what we'll prove is that by induction on alpha, we will show that there are a eta in omega to less than alpha, k I less than alpha, and phi I, yi, I less than alpha, satisfying A and B plus 2 conditions. So C will be the condition that if we look at the all zeros path, 0 I up to alpha, that has the same type over the sequence we're given. So I less than or equal to alpha, or sorry, let's say less than alpha. So recall, when I say we're assuming 2, I mean, we're assuming we're given a sequence of tuples and formulas and tuples and formulas. And so what I'm saying is that I want the all zeros path of the tree that I'm building to have the same type as that sequence that we're given. And D is that this tree of tuples, eta in omega to less than alpha, is S indiscernible. Okay, so instead of just getting 1, we're going to get 1 with 2 additional conditions, namely that the all zeros path has the right type, and then also that that we have S indiscernible trees. Okay, so for alpha equals 0, there's nothing to show, because all of our non-trivial conditions talked about the level I plus 1. So you just take any formula. I mean, there's nothing to show. So now assume for alpha, and assume we are given a I less than alpha plus 1, and a sequence of formulas phi I x, sorry, yi I less than alpha plus 1, such that phi I plus 1 x a I plus 1 divides over a sub less than or equal to I for all I less than alpha plus 1. Okay, so then by induction, there is a tree, a eta in omega to the less than alpha, satisfying the conditions A, B, C, and D for AI I less than alpha and phi I less than alpha. So if I look at my sequence of tuples and I look at my sequence of formulas up to alpha, so I forget the last one, then the inductive hypothesis will tell me that I can build a tree now of height alpha such that paths are consistent, children of a common node are inconsistent, and the degree of inconsistency depends on the level. And additionally, the tree is S indiscernible, and the all zeros path has the right type. Okay, so let's draw this picture, and this will be the last thing we do. So let's draw the picture for 2. So let's suppose that alpha is 3, and I know that for a tree of height 2, I can find a tree like this, such that this blue thing has the right type. It has the same type as the sequence I was given. So pick an element, let's call it, well, I don't know, let's call it A star, such that if I look at A sub 0 to the less than alpha, comma A star, this should have the same type as A less than alpha, comma A alpha. So this is always possible. I mean, I knew that A0 to the alpha had the same type as A less than alpha. So I just pick an A star such that it has the same type. You can always do this. Then, by assumption, because phi alpha divides over over what? It divides over A less than alpha. We know phi alpha. So I guess I should say I'm assuming alpha is successor. Otherwise, nothing to do. Okay, so we know phi x alpha x A star, sorry, because phi x alpha divides over A less than alpha, we know that phi x star A star divides over A0 to less than alpha, because they have the same type. So, you know, if B divides over C, then B prime will divide over C prime if B prime and C prime have the same type as B and C. So just by an automorphism, I know that I have this fact. So there is an A 0 to less than alpha indiscernible sequence I, which is A star I less than omega, with A star is equal to A star 0, such that phi x A star, sorry, this should be phi alpha, A star I less than omega is k inconsistent for some k. Dividing just says that it's inconsistent along an indiscernible sequence, but if you're inconsistent along an indiscernible sequence, then you're k inconsistent for some k uniformly. So what we'll do is we will call k alpha plus 1 k, or call k alpha plus 1. Give it this name. Okay. And I actually mean alpha. Sorry. Okay, so now what do we do? Now by S indiscernibility, for each eta in omega to the alpha minus 1. Okay, this is really annoying. I'm sorry. So remember I said that alpha is successor. Otherwise, there's nothing to do. I mean, so our conditions are trivial if we don't deal with the case that alpha is successor. So I'll write this carefully in the notes. But okay, if alpha is a successor, then alpha minus 1 makes sense. You just choose the thing of which alpha is the successor. Then there is some sigma sum eta such that sigma eta of 0 to the I is equal to A, sorry, what do I mean there? I mean, A sub 0 to the I is equal to A sub sigma up to I. So what is this saying? If I'm looking at my tree, then if I look at the tuples along this path and the tuples along this path, they have the same type by S indiscernibility. So that means there's an automorphism that takes this one to this one. And we're going to call that automorphism sigma sum eta. It's not unique. There might be more than one, but we can pick an automorphism that takes the zeros path to this. So now what we'll do is we'll define a tree. B eta, eta in omega to the alpha, such that what do I want to say? I want to say that if eta is less than alpha, then A eta equals B eta. So if it's not of the highest level, I don't change anything. I leave it as before. And if eta is in omega to the alpha, if it's at the highest level, then I define B sub eta. Okay, let me say it this way. This is a bit annoying, I'm sorry. Okay, so if I have eta concatenated with J is in omega to the alpha. So remember, eta was an element of omega to the alpha minus 1. So I'm going to write anything of level alpha can be written as something omega to the alpha minus 1 concatenated with an additional element. So this is the sort of general form. Then B eta concatenated with J is going to be equal to sigma to the eta of A star J. Well, this is really hard to figure out what's going on, but let's draw the picture. So I had my all zeros path, and then at the top I had this new indiscernible sequence. So this thing here is what we were calling A star J, this sequence. Okay. And now what I'm saying is, if I have some other path through my tree, I want to define its omega successors now. So this path, I'm going to call this eta, and I want to define its jth successor. How do I do that? Well, I look at the automorphism that takes me from the all zeros path to this path, that's sigma sub eta, and then I just let the jth element on top be the image under this automorphism. So now we know B eta, eta in omega to the alpha satisfies A, paths are consistent because the path of the all zeros path was consistent. And every other path is going to be an image of that all zeros path under an automorphism of one of the all zeros path together with one of these new formulas. B is satisfied because either you are children of a common node that was already in the old tree, or you are at the top where you know that you're an image of this indiscernible sequence and you are inconsistent along that indiscernible sequence. You also satisfy, I can't remember, I guess C, which said that you have the type of the all zeros path as the same as the type of the sequence you started with. And then to satisfy D, that you're indiscernible, replace B eta, eta in omega to the less than or equal to alpha by an S indiscernible tree locally based on it to satisfy D as well. So D just said that it was S indiscernible. Okay, you can do that just by replacing this with something which is S indiscernible, and the properties that you need are clearly preserved. And that's the proof. So this says chains of dividing are equivalent to trees of a certain height, and that uses S indiscernibility. And using that, we will be able to prove local character in Kim's lemma. So I guess it's going to take another time, but I think it's good to see these arguments because this kind of automorphism argument where you really do something on the zeros path, and then you sort of copy it everywhere else in the tree using automorphisms. This happens all over the place. This is a really common kind of argument form. So it's worth doing it in some detail. All right. I guess we're going to stop there.